take.
Oh, he can so take this.
He said he could.
I don't think so.
I
don't think he could.
Wait, against what, like a running group?
No, like in a play.
Like a Mortal Kombat.
All right. So dot products. So far all we've talked about with vectors is addition and subtraction and scalar multiplication. Dot product is one form of vector multiplication. Next time we will learn about the cross product, which is another form of vector multiplication. All right, our definition.
Dot product's easier.
Yeah, the dot product is the friendly one.
Is dot product the one that gives you a scalar?
Yes.
Then dot product's easier.
Oh, yeah.
So we're going to say that V in component form is V1, comma V2. I'm going to say V3. I'll just jump straight to a three-dimensional vector.
All right.
And U is U1, comma U2, U3. V dot U. And we call it the dot product because we show the multiplication with a dot, is V1 U1 plus V2 U2 plus V3 U3. If we just had a two-dimensional vector, we would just have the first two there. And this is, each of these components is a real number, so this is a scalar. We do not get a vector out of a dot product. Now it is a very simple operation, but the dot product contains a lot of information about those vectors. And we're going to talk about what that information is in just a little bit. You'll also hear this called the scalar product. And in the context, when you study linear algebra, you can represent vectors as matrices. You'll also hear it called the inner product. So just a couple of different terms. Scalar product is more common than the inner product. Inner product is a little more specialized terminology for it. Dot product is pretty common. All right, so easy operation to perform. Let's talk about some properties. So properties of the arithmetic of dot products. Dot product commutes. So U dot V equals V dot U. Not everything commutes. We're used to everything commuting, but not everything commutes. Dot product does, though. We can distribute a dot product. U dot V plus W. We could add these together and do the dot product, or we could do U dot V plus U dot W. So dot product is distributive. Scalar multiplication. If we multiply the dot product by a scalar, that is equivalent to multiplying either of the vectors by the scalar and then doing the dot product. And C here is a scalar. 0 dot any vector is 0. So the 0 vector dotted with any vector is 0. This next one turns out to be one that comes up a lot. It's an important one. If we dot a vector with itself, U dot U is the magnitude of u squared. So if you think about how we form the dot product here, if this were u dot u, you'd get u1, u1, u2, u2, u3, u3. So u1 squared, u2 squared, u3 squared, which is the square of the magnitude.
Wow.
This comes up a lot when we're coming up with equations that have to do with vectors, and we want to simplify them. Yeah.
Is that zero vector?
Nope. This is a zero vector. This is a zero scalar. Because the result of a dot product is always a scalar. All right. So are we good with the properties? So the geometry of the dot product, that's really what's important to us. We'll talk about that in just a second. If 0 is less than or equal to theta, less than or equal to pi, where theta is the angle between u and v, then, so let me draw a picture here. So we just have two vectors like so, and theta is the angle between them. That's a big point where they intersect. U and v. The cosine of the angle between the two vectors is u dot v over the magnitude of u times the magnitude of v. Or, the other way we can write this in a different form, u dot v equals the magnitude of u times the magnitude of v times the cosine of theta. This comes from the law of cosines. And we're going to take a look at that in just a second, because going through that process is instructive in how we use the properties of dot products, how we use vectors to show things. But from this equation, u dot v is the magnitude of u times the magnitude of v times the cosine of theta. So what this tells us, I'm going to draw another picture here. If this is u and this is v and this is theta, and we project this down here, this length is the magnitude of u times the cosine of theta from this little right triangle. So what the dot product tells us is the product of the amount of vector u that's in the direction of v times the length of v. So it's kind of multiplying the amounts of vectors that are in the same direction. So that's what the dot product really is we're taking one vector and seeing how much of it goes in the direction of the other vector and multiplying those two quantities. And that's one way that we're going to apply the dot product. Because what's another context where we're interested in how much of a vector goes in the direction of another vector? The component. So if we're talking about work, for example, we're interested in how much force goes in the direction of motion, because that's the amount of the force that does work. The dot product comes up in the context of work. And we'll use it in other similar contexts where we want to know how much of that vector is in a particular direction. All right, so let's look at why this works. This is a nice little demonstration with the law of cosines. All right, so I'm going to draw this picture again. And we're going to put another vector. There's v. And I'm going to put a vector here. Well, that vector, because of the way that we talked about adding and subtracting vectors, this vector is u minus v. And we're going to look at this triangle. There is theta. From the law of cosines, says that the magnitude of u minus v squared is the magnitude of u squared plus the magnitude of v squared minus 2 magnitude of u magnitude of v cosine theta. That's a law of sines applied to that triangle. Well, we just talked about this property that u minus v magnitude squared is u minus v dot u minus v. Whoops. And now we're going to distribute. We know that the dot product is distributive, so this is u dot u minus u dot v, this shouldn't be a dot, that should be a minus, minus v dot u plus v dot v. So we're just foiled that out. Well, what is u dot u? Magnitude of u squared. And we know that u dot v equals v dot u, so that's minus 2 u dot v. And this is plus the magnitude of v squared. So we're going to set this piece equal to this piece, because this is magnitude of u dot v squared. And when we do that, we see that the magnitude of u squared minus 2 u dot v plus the magnitude of v squared equals, do you see what's going to happen here? Magnitude of u squared plus the magnitude of v squared minus 2 magnitude of u magnitude of v cosine theta here. Well, this we can subtract, this we can subtract, and we can divide by negative 2, and we get that u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between them. From law of cosines and our properties of the dot product. So this is this type of argument using the properties of our dot product. We'll do the similar thing with properties of cross products. When we start talking about acceleration and velocity and tangential acceleration and normal acceleration, this kind of argument is what we do to come up with our equations. All right, we good so far? Really, the gist of this is the dot product tells us geometrically something about the relationship between those vectors. Something about how much of one vector is in the direction of the other vector, and we multiply those quantities together. It also gives us some information about the magnitude, about the magnitude of that relationship. Let's put it that way. So we know that the magnitude of u and the magnitude of v are greater than 0. So if we have vectors situated like this, the cosine of an acute angle, positive or negative? Positive. So if the angle between our two vectors is acute, u dot v is greater than 0. Because the magnitude of u and the magnitude of v are positive. And the cosine is positive. If we have an obtuse angle between our two vectors. So there's theta. The cosine of an obtuse angle, positive or negative? Negative. U dot v is less than 0. So geometrically, that's telling us that the component of u in the direction of v is in the opposite direction. And this is the most important relationship that the dot product tells us about geometrically. That's a 90-degree angle. Cosine of 90 degrees. 0. U dot v equals 0. This last picture tells us that if u dot v equals 0, the angle between the two vectors is 90 degrees. So that tells us that in this situation, there's no component of u in the direction of v. In this situation, we say u and v are orthogonal.
Orthogonal.
So if the angle between the two vectors is 90 degrees, we say that they're orthogonal.
Are we gonna have to like this?
And we will, over the course of the end of this semester and next semester, we'll use 3 different words to mean 90-degree angle. So orthogonal refers to vectors in relation to each other. We usually use perpendicular to talk about lines and planes in relation to each other. And we will use normal when we talk about vectors with lines and planes. And I'll say surfaces. All of them mean, they make a 90-degree angle with each other, but we use the different words in the various different contexts.
So that's 2 more words that I need to know.
Yeah, that's what I'm saying. Have the 2 colors and like.
Oh, is that why I have to
All right. So this always happens. We'll talk about these things and we'll get some kind of question that asks about the angle between vectors, and students forget that we can use a dot product to help us find the angle between vectors. So when you see a question that involves angles between vectors, you should think dot product. So I'm not going to go through a lot of examples of calculating with the dot product. Calculating with the dot product is very easy. So I don't think I need to demonstrate that. One of the important applications, and was it Brody might have mentioned it, someone mentioned it, with the dot product has to do with vector projections and vector components. So let's talk about projections. All right, so what we're interested in here is kind of extending the idea that I was talking about earlier. So I'm going to draw a couple of vectors. And I'm going to say this is u, and this is v. And what we want to do is figure out the component of u in the direction of v. And I'm going to call that, and we're going to turn that into a vector. So that vector is going to be, in our book, they use a notation W1. And we also want the vector, I'll do that in a different color, that is orthogonal to V. So I'm going to project that, so we're projecting this over at a 90-degree angle, W2. So W1, and I'll do this in blue just so we see we're extending this. There's my blue, and there's my blue arrowhead. So we're interested in the component, the vector component of u in the direction of v, and the vector component of u orthogonal to v. And from our drawing, we can write that the vector u equals W1 plus W2. Can we think of the physics people here? When would we be interested in the component of something in the direction of a vector and the component of something orthogonal to the vector?
The direction is moving that way, and then orthogonal is...
What's that? So we're talking about the motion orthogonal forces when it definitely has to do with forces.
Orthogonal also helps you when you're working with circles. Anything that's rotating.
Circles, rotation. That's so. Yep, we're on the right idea. What does the let's think about acceleration. What does the acceleration in the direction of motion do? Speed you up or slows you down depending on the sign. What does this component of acceleration normal or orthogonal to makes you turn? So this is going to be we're going to use this idea when we break acceleration into a tangential component and a normal component. So we want to figure out how much of the acceleration is speeding us up or slowing us down, and how much of the acceleration is changing our direction. And this normal component of acceleration, the changing direction, is going to have to do with the curvature of the particular curve that we're talking about. So we're building up a vocabulary so that we can talk about these things. But one of the most exciting to me, one of the most exciting is in chapter 12 we will quantify curvature. So we'll define a number that tells how curved something is, which is kind of a cool idea. To me, it's a really cool idea. All right, so what we're saying here is that W1 is parallel to V, and W2 is orthogonal to V. We call W1 is the projection of U onto V, or along V. So the projection of U onto V, and notice these are vector quantities that we're talking about, or you will also hear it called the vector component. of u along v. And we write, the notation is kind of strange. So we say that W1 equals the projection onto V of U. So projection onto V of U. The subscript is a vector that we're projecting onto. And we can say from this equation, or we can also see from the diagram, that W2 is U minus W1. And this is the vector component of U orthogonal to V. So what we're interested in here is breaking our vector into a vector component that's parallel to a particular vector and another component that's orthogonal to that particular vector, so that those two components add up to U. So the tangential component of acceleration and the normal component of acceleration add up to the total acceleration, for example. Well, how are we going to find these? Well, didn't we just talk about this idea?
Yes.
Isn't that related to the dot product? That quantity of U in the direction of V? We find it using the dot product. So we're going to say we find W1 using the dot product. Really, any time that we're interested in how much of a vector is in the direction of another vector, that's going to be a dot product process. So here's the picture that I drew before when we were talking about the geometric interpretation of the dot product. This scalar quantity is U, magnitude of U, cosine theta. And U cosine theta, magnitude of U cosine theta, from our equation of the dot product, is U dot V over the magnitude of V, because I'm missing the magnitude of V there. So that little scalar component is U dot V over the magnitude of V. Well, we want a vector in that direction, in the direction of V, with this magnitude. Well, how do we find a vector in the direction of V and give it that magnitude? We want to find a unit vector. So a unit vector in the direction of W1, because this vector is W1, is V over the magnitude of V. So I can write W1 is U dot V over the magnitude of V times V over the magnitude of V. And usually what we write, or the way that you'll see it written, is U dot V over the magnitude of V squared times V. And from what we just talked about here, this is the same as the magnitude of u times the cosine of the angle between them times v over the magnitude of v. This is the magnitude of that component, and v over the magnitude of v is a unit vector in the direction we want our w1 to go. So what we found is this length, this scalar length, and multiplied it by the unit vector in that direction. So the formula that they give you in the book is the projection onto v of u is u dot v over the magnitude of v squared, this is what you'll see in the book, times v.
But you could also use a cosine.
And we could also say that's also equal to u, magnitude of u, cosine theta, times v over the magnitude of v. You would use the first one if you don't know the angle between the vectors. So you know the two vectors. Here, if you know the angle between the vectors, then you don't have to, you're pretty much done. So yeah, in this form, we do not need to know the angle between the vectors. In this form, we would need to know the angle between two vectors. And W2 is u minus W1. So finding that component in the direction of v is the key, because then we know two of the three quantities we can subtract to get the other one. All right, I just want to go through a quick example of calculating these vector components, and then we'll be done with dot products. So I'm going to say B. I'm going to use A and B just to keep my notation a little cleaner, because my U's and B's tend to look the same. We want to find the projection onto A of B and the vector component of B orthogonal to A. All right, so we're just going to go through our process. The projection onto A of B, and I'm going to say that's W1 in our notation, is we're just going to do B dot A over the magnitude, since we're projecting onto A, of A squared times A. Well, B dot A, what is B dot A? Six minus 1, 5. The magnitude of A is square root of 3 squared plus 1, so square root of 10. So let's say A squared, magnitude of A squared is 10. So W1 is B dot A over the magnitude of A squared is 1/2 times A. And then I could write it as 3/2 I hat minus 1/2 j hat. And W2 equals B minus W1. So we get 2 I hat plus j hat minus 3 k hat minus 3/2 I hat minus 1/2 j hat. And when I do that, I get W2 equals 1/2 I hat plus 3/2 j hat minus 3k hat. Yes.
Is that when you said the very first equation, is that dot A or times A?
Times A.
So how do you tell the difference?
Well, because this quantity is going to be a scalar. Right.
The left side is the scale.
So I'll make this dot smaller. There.
Oh, so there's never a situation where it could be both.
Right, right. All right, is W1 in the direction of A?
Yes.
How do we know? It's a scalar multiple, right? W1 is in the direction of A because it's a scalar multiple of A. Is W2 orthogonal to A? How would we tell? The dot product. W2 dot A is 3/2 minus 3/2 minus 0, which is 0. So W2 is orthogonal to A because the dot product is 0. And we could also check if we added W1 and W2, we could check and we would see that they add up to give us B. So we want to feel special.
Yeah. God,
We like,
God.
mathematicians like giving new names to things.
Yeah, God.
So orthogonal has to do with orthogonal has to do with vectors.
I feel like it's making a problem that is.
It could have been just.
All right, questions? All right, so our homework page.
That's it's always helpful. I've never seen such a squiggly lines. Wow. Are we doing some activity now?
Yes.
Gross.
Is this our Untitled project? Are we that time we're going to slash this?
Yeah.